Exam 1, problem 6. A man with a mass of 80 kilograms trying to push a 100 kilogram cart up a ramp at 15-degree angle is shown in the figure below. What is the man's weight? All right. So part A, what is his weight? Well, his weight is his mass times the acceleration of gravity, which is 80 kilos times 9.8 meters per second squared. All right. And that's going to give us his weight is 80 times 9.8, 780 newtons. All right. Part B. What is the normal component of the man's weight pointed directly into the ramp? Okay. So here, the ramp is at 15 degrees, right? The man's weight points straight down towards the center of the earth. So what is the component of it straight into the ramp? And the component, this angle, is also 15 degrees. So if you have to figure that out, here's what I imagine in my head. Imagine closing down the ramp. What happens to the angle between the normal and straight down? Eventually it goes to 0 as this angle goes to 0. Right? So this angle, the 15 degrees, and that angle are one and the same. All right, so the normal force for the man is the man's weight, 780 newtons, times then the cosine of 15 degrees. 780 newtons times the cosine of 15 degrees. All right, so 780 times the cosine of 50 radians of 15 degrees. 753 newtons or 750 newtons. 750 newtons, right? That's the normal component of his weight straight into the ramp. How much of the man's weight points down the ramp, right? Parallel to the ramp. So that, I'll just call it force parallel. That is 780 newtons times the sine of 15 degrees. All right? Okay. Equals 784 or 780 newtons times sine radians 15 degrees. 202, so 200 newtons. 200 newtons, right? Okay, part D. How much of the cart's weight points down the ramp? All right, so for the cart, let me do FP cart. I'm going to call this FP man. All right. The parallel component of the cart's weight is first its weight, which is, how much is its mass? 100 kilograms. Okay. 100 kilograms times 9.8 meters per second. Meters per second squared is its weight times, all right, we're asking for the component straight down the ramp. So that is again times the sine of 15 degrees. All right. Okay. So 100 times 9.8 times sine of radians of 15 degrees. 253 or 250 newtons. Right? That's how much of the car's weight points down the ramp. All right? Okay. Part D. Part E. Assuming the coefficient of friction between the man's shoes and the ramp is 0.7, will the man be able to push the cart up the ramp? All right. So what is the maximum frictional force this man can exert? Well, it's his normal force all right, times the coefficient of friction, static friction, right? So the 0.7 is the coefficient of static friction. His normal force is 750 newtons. So 0.7 times 750 newtons is the maximum force he can exert. Call it 530 newtons, keeping our significant figures correct. 530 newtons is the maximum amount of force he can exert before slipping, right? Okay. Will the man be able to push the cart up the ramp? So what is the total force down the ramp? Total force down the ramp is the weight of the man plus the component of the weight of the cart, right? Both of those point down the ramp. So that's 200 newtons plus 250 newtons, right, is 450 newtons. So the answer is the man can push the cart because why? He has 80 newtons of force to spare before he starts slipping. Okay. Now, part F. If it rains, coefficient of friction drops to 0.5. What will happen? So if it rains, coefficient of friction drops, all right, to 0.5. 0.5. So 0.5 times 750 is 380 newtons. Right? It's 380 newtons. The man still has to support 450 newtons, so if it rains, the man starts slipping backwards. All right, that's it for the final problem.